All right, good morning. Appreciate the opportunity to come and share information with you guys. I'm going to talk about, so I'm affiliated with the Joint Center for Energy Storage Research. I'm going to talk about work going on within this project or this program, and specifically I'm going to focus on a materials-based redesign of the lithium-sulfur battery, and this will be a bit more electrolyte focused. Let's see, the primary message that I want to get across to you, remind you of, is in the sulfur system, we are essentially positioned, we do energy storage and release by two solid end members, and in between those two solid end members, we rely on a self-mediated redox mechanism for creating lithium polysulfides, right? And so electrolyte plays a really key role here, and this is one of the reasons why we are currently using, why the community is currently using largely a single electrolyte, and it's highly solvating. And we're going to talk about an alternate approach. From our perspective, lithium-sulfur is really at a crossroads. What we refer to as the conventional approach, which is highly solvating mixed ether system, right, the DAL-DME that we're all familiar with, and modification of cathode, right, to play this game of containment, whether it's encapsulation, strong absorption, leads to an outcome that we think is limited commercialization. And in order to be able to expand that, leapfrog, create new application space or promise for lithium-sulfur, we see two different outlets. One is the solid-state lithium-sulfur. We're working in that area. There's been some nice talks that that I sat in on yesterday, where others are working on that area. But we think the primary area is still this idea of liquid electrolytes. We are arguing one needs a multi-pronged approach where you integrate best-in-class concepts. So a lot of the materials we may already have. There may be some degree of fine-tuning that is necessary, primarily from the system integration level. And from our perspective, it's really about managing dissolution and precipitation, this chemical transformation or conversion reaction that's happening with sulfur. There are some constraints that apply to this, and we'll talk a little bit about those. The way to think about this is we have experience in this area, in the emergent area, highly solvating systems where we look at, or the community is looking at, a sister chalcogenide, which is the lithium oxygen system, and this ability to mediate the superoxide intermediate, to manage it. This is analogous to what we're doing with the polysulfides. But there's this other area that we refer to as sparingly solvating that we have lots of experience in, right? 100 years or more in lead-acid batteries, where we're reliant on a very low solubility product to keep, so essentially insolubility, to keep products, lead sulfate, directly against an electrode surface and harvest all of the energy that we've released or harvest all the energy that we've stored. So there's analogies here. JCESR's goal is to simply increase, maybe not simply, but conceptually, simply increase the cycle life while hitting a relatively large or high energy density or specific energy target. So somewhere around 400 watt-hour per kilogram, 400 watt-hour per liter. This inverse curve, the harder you push the system in terms of, in terms of cycle life, right? The practical capacity or energy density that you can build systems that begin to fall off. So we're trying to level that curve so now that you can achieve something like 1,000 cycle life out of a higher 400 type energy density value. All right, so we have three key challenges we have to overcome in order, I should say these are eminent challenges. There'll be others that follow this, but these are how we've rated the barriers that currently exist. The first of those is we're not moving forward until we do lean electrolyte. The volume and mass of electrolyte that's being used in lithium-sulfur today will not achieve the energy density targets that are necessary. We're dealing with the lowest density phase, so you can immediately see the connection with the error in targeting high volume ratios of the electrolyte. We have to drive well beyond where research is happening at the 90% volume fraction, or 7, 8, 9, 10 milliliter per gram of sulfur, sometimes even much greater than that. And we've got to move up this curve to something like 2 or less milliliter per gram. And we'll refer to that as an ES ratio. Second thing we have to worry about is capacity and utilization, right? So the bottom line is we're not moving forward unless we're running in this 6 to 8 milliamp hour per squared centimeter aerial capacity. That's where you need to be. If you do the techno-economic modeling, that's what the modeling outcomes are. And you can achieve that in several different ways. You can do higher utilization, meaning closer to theoretical, or alternately, you can do this with thicker cathodes. But that's got to happen. And then the last thing that we need to be able to achieve is stable lithium anodes. And we want stable lithium anodes for two reasons. The first is obvious. We want limited excess to achieve long cycle life. The other one isn't so obvious, and that is at modest coulombic efficiencies, meaning something less than 99.9%, which we're not at now in lithium sulfur, the bottom line is that you consume the electrolyte. And if you're sitting at low to E to S ratios, the more precious material in the battery itself is the electrolyte and actually not the lithium. All right, so how are we pushing forward on lithium sulfur? Our strategy is we'll make advances by learning how to integrate critical materials concepts. We're working on all of these areas. So the labels in red that you see are specific targets, right? Interface design for cathodes and anodes. This idea of electrolyte design, how we can better manage precipitation and dissolution. Cathode architecture is a critical issue primarily for maintaining both ionic and electronic connectivity, right, to the solid-state end members that we're trying to access. And then redox mediation, right? The bottom line is that if we're going to play games with lithium polysulfide concentrations, we're going to have to augment redox mediation. So we're working in all these areas, but we can make a little bit more knowledge transfer progress if I focus on one specific area. So I'm going to talk about strategies for redirecting reaction pathways in the lithium sulfur system. So the concept of a sparingly solvating electrolyte was born out of the thought that if you have to drop the E to S ratio to such low values, you're always going to be operating in this saturated mode, right? And in that regard, something that has high solubility for lithium polysulfides versus low solubility, there isn't much of a difference between those two because we're always in this saturated case, right? The only question is how much material we've got sitting in the liquid phase and what its residence time is. So we see an opportunity to manipulate this. We published a paper, a perspectives paper, defining what we meant by the concept of sparingly solvating, and more importantly, what you could do with an electrolyte that would achieve this specific property, right? And one of the outcomes of this is the clear identification that these solvent and salt systems, very high salt concentrations in a solvent system, maybe a single solvent, maybe a binary solvent, and in this case highlighted by the acetonitrile instance, right? So what's really remarkable about the acetonitrile system is that you can cycle lithium in it. You'll know that if you've ever tried to use acetonitrile as a solvent, that you electropolymerize the acetonitrile in the presence of low, modest salt concentrations, that problem disappears. It's not completely eliminated, but it disappears in these solvent and salt systems. All right, so this idea that I'm going to describe to you a little bit turns on its head the idea of a non-solvating system. So we've all read the literature, you're familiar with Watanabe's work, you're familiar with Lyndon Nazar's work, and this idea of using what was referred to at the time as a non-solvating electrolyte. So it's that exact same acetonitrile in a 2-to-1 relationship, molar relationship with salt, and a hydrofluoroether added. This is the acronym is TTE. This is a pseudo-symmetric tetrafluoral ethyl tetrafluoropropyl ether. The bottom line is that you can tell from the discharge curves alone that there's a radical difference between these two systems. So something different is happening. One can look at separators taken from, which are these images, and show that there's very little polysulfide, if any, detected in those systems, and the solubility for sulfur and polysulfides in general is somewhere below the detectable UV-Vis cutoff. So this is where our story begins, sort of the new stage of this, and that is this idea of sparingly solvating as opposed to non-solvating. It turns out that solvation does take place. It takes place at very low levels. We'll talk about that a little bit. But the most remarkable thing is what happens to the discharge curve when you elevate the temperature in this system. So you go to 55 degrees, and you can see this red curve. The black curve is the black curve is DAL-DME with 1 molar lithium TFSI, and there's been no lithium nitrate added as a passivant for the anode. In the case of the acetonitrile, so you get the classic two-plateau behavior, right? In the case of the acetonitrile solvate system, we get a single plateau. And there's some details about this, 3 critical details. The initial potential is about 2.2 volt. This is lower than the 2.3 volt required, or that signifies or signals the conversion of sulfur to long-chain polysulfides. So we already know that we're not producing long-chain polysulfides in this system. Then we get this potential excursion, and I'm going to show you that that's an overpotential. And then we come back up in potential, and actually the mid-range of that curve has a potential that's several tens of millivolts higher than the 2.2 value. Comparisons of capacity are shown here, and of course the DAL-DME gives terrible response because you don't have any lithium nitrate present in the system, whereas one can do sustained cycling in the acetonitrile system. No color changes. The bottom line is that the system is controlled by a combination of kinetics and mass transport. That's shown clearly here. You'll notice an enormous similarity between variable temperature increasing from blue to red, from room temperature to 70 C, and then that similar but inverse relationship from 1C to C over 30 rate from black to red. Clearly, we're dominated by kinetics. As you slow things down, as you increase decrease viscosity and mobility in the electrolyte, you start to see this characteristic single plateau feature. Galvanostatic interrupt experiments tell us something about equilibrium potentials. So the key takeaway here is that in the green trace line at 55 degrees, you'll readily notice that we're starting at 2.2 volt. You'll notice that we don't see the dip relationship, so that's clearly kinetic, not thermodynamic. And then we come up to a higher potential in this mid-range, right? So we're doing 2 discrete reactions. The first is I'll demonstrate to you as what we refer to as a solid state reaction. The second is solution redox mediated. 30 degrees, the exact same potential is seen, right, at the early stages when you slow this down into an interrupt experiment. And no difference in terms of the sulfur, how we've loaded sulfur into a carbon cathode, whether it's a physical mixture, its infiltration into a mesoporous material, or in the case of Ketch and Black, a bit more microporous. You can follow XRD data and readily recognize now that there's a unique difference here. The disappearance of the sulfur on first discharge is much slower. There's an overlap region where sulfur actually coexists with the sulfide, and that's persistent halfway or more than halfway through the discharge regime. And then when we reverse and come back and charge, we form sulfur at an earlier stage, and you might also notice that we now are forming the alpha stacking as opposed to the beta stacking. So clearly, electrolyte plays a key role in this. X-ray absorption spectroscopy really nails the idea that we're forming short chain polysulfides in that first 400 to 500 milliamp hour per gram regime. You can tell that by looking at the sulfur K edge. This yellow colored peak that you're seeing there are the terminal sulfur anions, right, that have undergone discharge or reduction, and then the following peak are the center sulfur linkages. So we're dominated by this short chain polysulfide. We can develop a kinetic model and explain generally what we're seeing. That is, this first 2.2 reaction is a solid state reaction between sulfur and the formation of a short chain polysulfide. We're arguing based on Faraday's law that that's an S42 minus. Eventually, where the dip occurs is an overpotential, where we've essentially produced our maximum amount of the S42 minus. We have to switch the reaction now. We have to drive some other reduction process, and now we're producing a critical mediator. We think it's Li2S6. It could potentially be the radical anion lithium S3 minus, or excuse me, S3. And the bottom line is that that plays a critical role in that fuchsia curve, rose-colored curve, right, that is showing constant presence, right? And disproportionation is also working at the same time because we're starting to produce sulfur again, right? So we have this mixed potential that's about 10, 20 millivolt higher than the first potential. Okay, so I want to describe to you why this works the way it does, right? So this is a work that goes after trying to rationalize how the solvate structure itself is, or composition is related to lithium polysulfide solubility. So we've taken an NMR technique, we've adapted it, we've looked at what happens as a function of solvent lithium salt ratio, in this case TFSI, lithium TFSI. And what you readily see is these two intersecting curves, right? So this is a plot of the Gutmann donor number extrapolated from NMR. You can see that we're out on a dilute regime where if we run far enough, we'll hit the value for what we understand Gutmann donor number is for based solvents. Slow decay, we hit a transition point, and then the donicity drops like a rock. And if you sample in a GIT-style experiment now, a point above that transition point where we start to decrease donicity and one below, you can readily see that we go from a two-plateau structure in the acetonitrile case to the monoplateau, okay? So it's clearly related to solubility and structure of the solvate. This is the difference in solubility for lithium polysulfides across the board, full speciation, right? And we've drawn the line for the acetonitrile case, and you can see what we're doing is essentially a seven-fold increase in solubility as we leave that solvate range and go into the dilute range, right? So it's really all about solubility. That's the dominant factor. There are some problems with running solvate electrolytes, and that is performance still remains an issue for us. We can get ideas by decoupling our anode, which is problematic, and I'll show you that in just a moment. We can do that by decoupling, where we build small pouch cells, and we use something like the O'Hara ceramic, this LTAP type material, as a single ion conductor to separate anode from cathode, use DAL DME electrolyte on one side, use our solvate on the other side, and we can sustain relatively large long-term cycling at reasonable fade rates. So we might refer to this 0.2% per cycle as an intrinsic fade rate for this specific composition of electrolyte. You can ignore the capacities because those experiments were simply done at with a lower loading cathode. We get higher capacity, and we can run up to 8 milliamp hour per squared centimeter in these types of tests. So early stage failure in these systems are largely dominated by the anode. Latter stage failure really has to do with the same sort of issue that we've been grappling with here, and that is stranded lithium sulfide within the cathode structure itself, which means that for our reaction mechanism, our reaction pathway, we may need to augment the redox mediation activity through a designer molecule in much the same way that Brett showed you the electrolyte genome helps identify what we should be synthesizing with JCESR. My last slide is just to drive home the point of, I think, that we've all been recognizing, and that is that everything about lithium is important. So having a very high salt concentration, having maybe unique attributes of structure of the electrolyte immediately adjacent to the lithium doesn't necessarily make you immune to the deposition process that takes place. So what you're looking at is 50 microns of lithium that's been cycled 10 times at these areal density and current density at a 3 milliliter per gram, one of our target values that we're starting with and moving down to 1. These, again, are 50 micron laminates, and every one of them shows this porous top cycled layer, right? And below is the reserve laminate layer that was originally 50 micron that's supplying our lithium. And what you can see is that there aren't huge differerences between the solvates for different compositions in different solvates, right? So we're running all the way from acetonitrile to something like digalime, a chelating electrolyte. THF is thrown in there. DAL DME only at room temperature, right? And higher E to S ratios. And the bottom line is that one always trends toward this more porous deposit structure. So that's why we believe that this protection is so important. We're not going to get it through the electrolyte alone. We're not going to get it through SEIs. I realize that might be a bit inflammatory relative to some people's work here, but quite frankly, these need to be artificially engineered structures that we're producing. I will gladly talk to you in person about some of the things that we're doing in that area. I need to end on this note. We've got a huge team, a lot of people doing a lot of work. One of the great things about being part of this team, other than working for George, is that there's such a great opportunity to tap into capability that runs all the way from very specific computational capability all the way out to some rather fascinating and maybe somewhat exotic characterization techniques that are absolutely necessary for moving forward. So thank you for your attention. I'd be happy to answer any questions.
Thank you, Kevin. We do have time for questions. Is there one? There's one, and another one. We'll take yours first.
Okay. Yeah. Hi, Kevin. Very good talk. Thank you. You talk about using this sparingly soluble electrolyte. So if you switch that to the earlier approach, where people using the ionic liquid to regulate the solubility, are you expect the similar result as you get from this electrolyte?
So. No, we do not expect the similar result. We haven't seen, I have not seen data published that would argue that you're on the path to doing this single plateau mechanism if you're using, I'm thinking about some of the, the PY14, PY13, TFSI systems, right? The sort of mixture systems that have been shown to help stabilize lithium somewhat. So I think, and I think the reason for that is has to do with the way lithium is coordinated. I think there's a very specific set of rules that have to be followed that relate to the coordination structure.
There was another question.
When you were using acetonitrile, did you see the reaction between the lithium and acetonitrile?
No.
No? No gassing or no anything?
Nope.
Okay.
Nope. Put lithium in there under dry conditions. Do your distillation, right, to clean, dry. Dry your salt as well as you can. Put a clean, say a pentane cleaned lithium laminate surface in that. Let it sit for several weeks, and it looks the same by the time you pull it out. Water is key.
Okay, Kevin, thank you so much.